So the final paper that you're going to see in this session is going to come from colleagues in Bremen. It is entitled Material Supply Strategy for Decentralized Assembly Control in Team Assembly, and it is authored by Torsten Sievers, Carsten Goldenstein, and Professor Kirsten Tracht. Thank you for sending that presentation and that contribution.
Hello and welcome to my presentation. The topic of my presentation today is Material Supply Strategy for Decentralized Assembly Control in Team Assembly. My name is Torsten Sievers. I'm from the University of Bremen, and there especially from the Bremen Institute of Mechanical Engineering. Besides me, also part of the paper are Carsten Goldenstein and Mrs. Professor Kirsten Tracht. The topic of my presentation today is about assembly control and team assembly. Team assembly typically used for large dimensional products. For example, you see here in the picture the assembly of an airplane. We have there some challenges. One problem is that we have a long duration of each assembly task, and also we have low reputation rates, and this is also due to we have an increasingly product individualization, so every worker don't repeat the task very often, and this leads to high demands in the control of the assembly processes. A possible option to deal with this situation is by using decentralized resource allocation. There was a development of a system based on bionic stimuli networks called mutualistic networks. This is basically the system how beans find the flowers in the nature. So each flower in the nature sends a stimuli, and the beans searching for the stimuli and find the flowers with the highest stimuli. We transfer this principle to assembly control. So each assembly task has or get an artificial stimuli. We see here in the right picture 3 assembly tasks with different stimuli. The stimuli will be filtered by different layers, for example, qualification and the existence of the material and material store. And then this information goes to a personalized graphical user interface, where a worker can select a task. So the worker see always a task with the 3 tasks with the highest stimuli, and the worker in the worker pool can select a task by their own, and then assign to a task, and the stimuli will be recalculated. During the validation of this principle, we see great effects, especially that the worker focus on their individual abilities, and also we have a higher motivation due to the free choice of the assembly task. And another great point is that we relieve our supervisors because they don't have to do the allocation and can focus on more important tasks. On the next slide, we see the graphical user interface on the right side with the 3 tasks the worker can select. Down the left, we see a typical situation where we have different tasks with different stimuli. This information will be filtered and then shown in the graphical user interface, and the worker can select a task and do the task and do this again. This is how the system principally works. We have or we solved some problems by doing this. The problem is material support. Because when we don't have or we don't know what the worker will select, actually at the moment we just have all the materials at the assembly station, so we don't have a problem with this. But of course this is not effective. We want to reduce our material store at the assembly station, because with a big material store we have long searching times and also need a lot of space. And another problem there is that we don't have a given sequence, so we just can provide the materials by sequence. And also we have another problem that we have, of course, transfer times from warehouse to material store, and we just know we don't know what the worker or which task the worker will select. So we have to find a better way there. We solve this problem by material supply through a kitting process. So on this slide we have on top here the generation also selectable assembly task the system will do. Then with this information we have we do a picking process where the sets of the materials will put together. Then we have the provision of the material at the assembly station, and after this, the worker will select the assembly task. There will be a short feasibility check if the material is there and the qualification is right, and then the assembly process can start. How this works in detail I have on the next slide. From left to right we see the typical process. We have first the stimuli calculation for each assembly task. So I don't said before, the stimuli just symbolize the importance of a task. With this information we can generate a list with each assembly task and the stimuli, and this information there go on the one hand to the filtering process for the personalized graphical user interface, and in between we do with this task picking the materials from the task with the highest stimuli and generates a set and bring it to this material supply, so that in the moment where the worker select, or even before filtering, we have the material and the material store, so we can also use the filter to check if the materials are there and only show the assembly task where the material are in the material supply. So then the worker can select the task and do the assembly process and do it, close the cycle. On this slide we see the typical, or our test bed. At the university we have there a test bed for large dimensional products with 3 assembly stations. At each assembly station there are materials, computer terminal for the user interface, and assembly area where 4 workers can work together. And also we have a material store on the right side. For validation of the material supply strategy, we use a discrete event simulation by plant simulation. On the top right, we see how we transfer the testbed into the simulation. We have an input where the assembly task come from. Then we have a material store for workplaces for each worker and a flow control who will be used especially for coordinating if workers work together at one assembly task here. And on the last we have an output. For realizing the material supply strategy, we have a subnetwork where the kitting process takes place. Also, we realize material support of small parts by Kanban-system. And we have there a buffer where the Kanban system or the Kanban parts wait for some sets to reduce the transports. And this is controlled by a flow control. And then the parts go to, or the sets go to each assembly station to the top layer network. The results show that if we change the selection behavior, so selection behavior is realized by geometric distribution. If we change this, we see that the maximum assigned worker, the frequency of this increases. So the the success probability just means if the success probability goes to 1, each worker selects the task with the highest stimuli, and so the frequency of max assigned workers increases in this case, and this is because of the calculation of the stimuli. So the stimuli has a structure-orientated component. This component looks how many tasks need this actual task to be done before start. And this component remain high, so if the worker select the task with the highest stimuli, and this leads to that the workers select the same task and do it with many people together. This also leads to another problem, that this due to the increase of the total amount of stock. We see the explanation on the right side here. So if we have a high success probability, the workers select the same task. So there are many sets in the material store. If the success probability is low, the workers select different tasks, and as a effect of this, of course, the total amount of stock is lower. Now we come to the summary. I showed you today a material supply strategy for a mutualistic assembly network and team assembly. For this, we combine kitting method with a Kanban-system. We realize this approach in a discrete event simulation for validation and see that we have an average amount of stock of 2 kits at each assembly station, but also we have a maximum stock level of 7 kits. Therefore, for further research, we have to integrate some restrictions on stock level or waiting times to further reduce our material supply area, And also we have to do a close look on the transportation time and of course the kitting durations to make the simulation more realistic. Thank you for your attention, and now I'm open for your questions.
Thank you, Torsten Sievers, for giving us this presentation and for submitting the paper. We're now going to take Torsten Sievers live for the question and answer. Torsten, hi from Berlin. Can you hear us?
Hello.
Thanks for joining us and for being with us. Thanks for the presentation and the paper. We are trying to discuss, or the discussion will go towards the implementation and the demonstration of the method that you investigate. In Bremen, I know you have a kind of learning factory. Can you tell us a bit more about this kind of demonstration case that you are looking for?
Yes, of course. So until now, we just do the simulation for the material supply strategy. And so the next step is to transfer this to our learning factory we have here in our university. I think I showed in the slides the layout of the learning factory with 3 assembly stations, and so the next step is to test our supply strategy. For example, during lectures here at the university. And after this, we hope we find maybe some industrial partners where we can do this with actual workers, because of course, when we do this with students from engineering, it's not quite the same as we do it with real workers, because they are more motivated normally.
Okay. So thanks for sharing these details with us right now. Thanks for sending the paper, and see you in the industry panel discussions in a minute.
Yeah, thank you.
Thank you. Goodbye. So this was the paper and presentation for the paper entitled Material Supply Strategy for Decentralized Assembly Control in Team Assembly, authored by colleagues from Bremen, Torsten Sievers, Carsten Goldenstein, and Kirsten Tracht, who is the leader of that group.